Hello students, today we will solve one question and the question goes like this. The question is having A and B part. In first part, a 900 picofarad capacitor is charged by a 100 volt battery. How much electrostatic energy is stored in the capacitor is to be found. Question B says, the capacitor is disconnected from the battery and connected to another 900 picofarad capacitor. What is the electrostatic energy stored by the system now? In the first case, we got a 900 picofarad capacitor and that is connected with a battery, and the voltage provided by that battery is 100 volts. In second case, this 900 picofarad capacitor is connected in parallel with another 900 picofarad capacitor. In both this configuration, in both this situation, we need to find the energy that is stored by these capacitor in the system. Energy stored by these two combinations of capacitor. From the capacitance topic, we know that energy stored in a capacitance is given by half CV square, and C is given as Q upon V, and by interchanging all these numbers we can find other values. Like in case we want to find the value of C and we got this and this, we can by interchanging U, V and C we can find the value of C. Similarly here, in case we want to find the charge, Q will be equals to C into V. So we will see the solution, how we will be dealing with such a problem. First of all, it is given to us that C equals to 900 picofarad. Picofarad is written as 900 into 10 to the power minus 12 farad. Pico gives us 10 to the power minus 12 units. In case 1, when it is connected with a battery of 100 voltage, charge on the capacitor is given by Q equals to CV. C is 900 and V is 100. Okay, 900 into 10 to the power minus 12 into 100, and the charge on it is given as 9 into 10 to the power minus 8 coulombs. 9 into 10 to the power minus 8 coulombs. That is the charge contained by capacitor 1 in case 1. Now we will go next. Energy stored is given as E equals to half CV square. C equals to Q upon V. We will introduce it here, half CV square. In place of this C we will write Q upon V. U equals to half into Q upon V into V square. This square and this V will cancel out and U will be half QV. This is what we have got. Okay. Now we will substitute the value of Q and V. We will substitute the value of Q and V. Q is 9 into 10 to the power minus 8 and V is 100 half. So energy we got over here is 4.5 into 10 to the power minus 6 joules. In case we are taking C and V, we will get the same answer. I will solve it for you to understand it better. See, U equals to half CV square. Half into C is 9 into 10 to the power minus 12. V square is 100 into 100. So 1, 2, 3, 4. 4 zeros will cancel the power to 10 to the power minus 8, and this 2 and 9 will cancel it to 4.5. So answer which we will get is 4.5 into 10 to the power half CV square, right? We will get it in the same format. Now see over here, this is the energy stored in the first case. In case 1, where capacitor is with a battery, and here it is not 9, it is 900, it is 900. That's how we are getting this answer. Okay. Now we will see the case B. In this two capacitor, one capacitor of 900 picofarad is connected with another capacitor of 900 picofarad. Okay, so battery of voltage 100 volt is removed and another capacitor with the capacitance value of 900 picofarad is joined, connected in parallel to the already existing capacitor. Now C1 equals to C2 equals to 900 into 10 to the power 12 farad. In this steady situation, the two capacitors have their positive plates. This is positive plate, both are connected in the same. Negative plate are connected with the same terminal. Okay. In this steady state, they have their positive plates at the same potential and their positive plates are on the, okay, this one is negative, again a wrong one. Negative plate at the same potential and their negative plates at the same potential. Okay, this statement is repeated from here. Let the common potential difference be V dash. Like, see, these are at parallel junctions. Okay, so in parallel what we have seen is our charge will be different. Our charge will be different in parallel. Charge will be different and our voltage will be same for both the capacitor. So we aim at a common voltage V dash for this and V dash for this, and the charge on each capacitor will then be Q dash equals to CV square. Q dash equals to CV square, sorry, CV dash, that is the common voltage which we have seen, and by the charge conservation Q dash comes to be equals to Q upon 2. How come Q upon 2? They have said the charge distribution is uniform among the two capacitors. Charge distribution is uniform. So we have applied the conservation of charge, that we are not losing any charge in this configuration. There is no loss of charge. Okay, so the charge is divided equally among the two capacitors. So Q dash is Q upon 2. This implies that V dash is V upon 2. Now if Q dash is Q by 2, then if we apply this in the formula, see on the down corner over here, Q dash equals to CV dash. Now Q dash equals to Q upon 2, then we will write Q upon 2 equals to C into V. Now what is the value of C? C equals to Q upon V, right? This is V dash. So Q upon 2 equals to C upon V into V dash. Q upon V, right? Then this Q and this Q will cancel and V dash will be equals to V upon 2. Hence we will get this one, V dash equals to V upon 2. Now the total energy of system will be U equals to half of Q dash V dash equals to 4 QV into this. So I will solve it for you on the next page. What it was given is total energy U equals to energy from capacitance 1 plus energy from capacitance 2. Energy from capacitance 1 is half Q dash V dash plus half Q dash V dash from the this one. ठीक है, यहाँ से ये आ रहा है और यहाँ से ये. Then there are 2 times this, 2 into half Q dash V dash. So this and this will cancel and we will get q dash into v dash. From the above we found that q dash equals to q upon 2 and similarly v dash equals to v upon 2. Okay, so we will substitute the value of q dash and q2 here. So we will find energy equals to q dash v dash equals to q upon 2 into v upon 2. So q v upon 4 will be the answer. Q v upon 4 will be the answer. From the total energy which we found out, total energy for system 1 was half QV, that was equal to 4.5. 4.5 into 10 to the power, there was some values. Okay, so this is what we have got from the first step. Now this thing can be resolved as 2 into half QV. Half QV's values is this. So sorry, this is not 2 into 1 by 2. 1 by 4 now. 1 by 4 can be resolved as 1 by 2 into 1 by 2 QV. 1 by 2 QV's value comes from here. Then 1 by 2 into 4.5 will give us 2.25 into some power values. Okay, so now we see that total energy is decreased. Total energy is decreased by half from system 1 to system 2. System 1 to system 2, total energy is decreased by half. See over here. Thus from going from A to B through no charge is lost. Constant or conserved. Conserved is a better term to be used. Conserved. Charge is conserved. For final energy is only half the initial energy. There is only change in energy. Only change in energy. So the question arises, where has the remaining energy gone? There is a transient period between the system settles to the situation B. During this period, a transient current flows from the first capacitor to the second. Energy is lost during this time in the form of heat and electromagnetic radiation. Now our system was like this. When we connected this C2 with C1, there was a small transient phase in which the charge was running from C1 to C2. When the charge was going from C1 to C2, some of the charge, some of the energy was lost in the form of heat and some in the form of electromagnetic waves as EMWs. Okay, so that's how we are left with only half of the energy in this system. So that's all in this question we need to understand and deal with. This concept is based on the conservation of charge in the combination of capacitors and knowing the amount of energy associated with the combination of capacitor and alone the capacitor. Okay, that's all for today's class. We'll meet up in the next class with something new. So have a good day. Bye bye.